Thanks so much for the invitation to speak, and it's a real honor to be here. And I want to say, both of my parents went to community college, and I just want to say thank you for what you guys do. I'm happy to be here. So I'm going to talk about climate resilience in cities, and really about three kind of global trends. Oops, yeah, thanks. Three trends that are happening. One is climate change. One is an increased rate of urbanization. People around the world are moving to cities. And the third thing here in the US, at least, is our aging infrastructure. So much of our infrastructure was built quite a long time ago. And thinking about what resilience means in that context, and I'll say a little more about that. So as an overview, I'm going to start with a big picture. Those three trends I just mentioned: climate change, urbanization, and aging infrastructure. And then I'm going to zoom in to the regional/urban scale and talk about what does climate change look like at a much smaller scale, focusing a lot here on the San Francisco Bay Area, because that's an area that I know a lot about. And then tell you a little bit about some of our research on resiliency and adaptation. So a little bit about the models and tools that we use, and then how we've used those to look at options for controlling heat events and also managing water. And then some conclusions. So just to kind of start it off and think about what do I mean by resiliency, I have this plot up here, which is from the National Oceanic and Atmospheric Administration. They have this database where they track billion-dollar climate and weather disasters. So in 2017, there were 16 such events that cost more than $1 billion each. And so you can see there are things like a couple of hailstorms, hurricanes, the fires in the West. And this is 2017, not 2018. So we know that there were more hurricanes and even bigger fires actually last year than the ones that are on here. And so what I mean by resilience is our ability to recover from these kinds of events and continue to be prosperous and have cities that work and thrive in the face of these kinds of events. And we've always, this is kind of a really abstract way of showing this, but we've always lived with extreme events and weather disasters, right? So we've lived in a world where things vary. Maybe this is the sea level rise, or maybe this is floods and droughts. And so over time, things vary, but we've been able to build our cities and build our infrastructure knowing that variation happens within some envelope, and that variation's around a mean state. But we're now living in a world where there's an underlying trend, and things are changing. And so certain extremes are getting more extreme, and certain extremes are becoming less extreme as the climate's changing. And you can kind of see that trend. This is the data for global mean temperature going all the way from 1880 up to present day, that the Earth is warming, and along with that warming are all sorts of other changes to patterns of precipitation and storms and sea level. So if we zoom in even closer at a particular, this talk is a lot about cities, so if you kind of zoom into LA, this is some data that some of our colleagues down at UCLA have. And so historically, the temperature has varied around, this is the average temperature for August. So it kind of varied around this very pleasant 75 to 80 degrees. Our projections for the future, kind of around the year 2050, are that's going to raise significantly, and that the kind of lower end of that variation will be above the historical mean. And an important point here is that it doesn't really matter too much which of these two scenarios are on. So the blue scenario here is one where we control our global greenhouse gas emissions pretty significantly, and the red one is where we just continue to emit without any limits on our emissions. And so an important thing here is that we're at this point in time committed to a certain degree of climate change. If we stopped all emissions right now, the Earth is going to continue to warm because there's delays in the system. And so as the ocean slowly warms, the planet's going to continue to heat up, and things are going to keep changing. But there's a huge difference after 2050, later in the century, which of these scenarios we're on. So if we have the scenario where we control our emissions, then that'll stabilize out and flatten out, and things will kind of reach a new equilibrium. If we continue to emit, then we're looking at a world in the end of the century where the low end of this is not even is even higher than the high end of the historical trend. So this is a world that it's really hard to understand what that world would look like because it's going to be so different from the one we're in now. So I think this is kind of an important thing. It kind of shows over the next 30 years this kind of double challenge that we have. One challenge is to adapt to the changes that are happening, and the other challenge is to limit our emissions so we can avoid this outcome from happening. So at the same time that those things are happening, the world is also moving towards greater and greater urbanization. So this plot is showing the sizes of different cities. And so the kind of big red circles are mega cities that have 10 million or more people. So in the US, we've got New York and LA, but there's all these emerging mega cities around the world. So people are moving more and more to urban areas. North America is the most urbanized region of the planet. So I think it's, 82% of North Americans live in what we would call a city, which I think includes suburbs as well. And as of maybe about 10 years ago or so, more than half of the world lives in cities. And as we go, by 2050, we think maybe about 70% of the world is going to live in cities. At the same time, here, particularly in North America, we've built so much of our roads and bridges and other infrastructure. A lot of our coastal infrastructure, energy infrastructure was built earlier in the 20th century, and now it's getting old and needs to be replaced. And so the American Society of Civil Engineers estimates that it's going to take $3.3 trillion to upgrade all of our infrastructure. And so if we're going to be investing this money to upgrade the infrastructure, these things are going to last for 50, 80, 100 years, these things that we're building. We really need to be thinking about how the climate is changing when we put them in when we build them, because they're going to be over their lifetime, things are going to change quite a bit. So now I'm going to just shift a little bit to what does climate change look like? And there's a really great, not every scientific community does this, but the climate research community has this practice of getting together and writing these assessment reports. And so there's been a number of these global assessment reports from something called the Intergovernmental Panel on Climate Change, where they synthesize these huge volumes, probably about this thick times 3. There's 3 of them that come out every 6 or 7 years that synthesize all of the research, everything that we know about climate change and its impacts. The federal government does this as well. You may have heard the most recent one of these national climate assessments was released on the Friday right after Thanksgiving. And then recently, the state of California has been doing its own assessments, and there's a state report, and I was an author on the regional report for the San Francisco Bay Area. And so this is the first time that we've had a synthesis report that's describing what we do and do not know about climate change at the level of one urban area. So I'm going to talk a little bit about that, and this report is one of 9 regional reports that were done for the state. There were 50 reports total on different topics. The report, this one report had 24 authors and 13 stakeholder reviewers. But before I get into the details, I wanted to talk a little bit about certainties and uncertainties with climate change. And so a lot of our information, some of it comes from observations and some of it comes from models. And so we have different degrees of certainty about different aspects of climate change. So we have relatively good agreement on those things that are related to changes in temperature. So we know that the planet's warming, and so there's pretty good agreement that there's going to be less snow in the western US in the future, because as it gets hotter, more of the precipitation falls as rain instead of snow. The snow melts faster. So there's a really good agreement among models and among scientists that there's going to be less snow. The harder thing is precipitation, because it's related in an indirect way to temperature. And it's quite variable to begin with. So just from a statistical point of view, precipitation is a more complex thing. And so there's big uncertainties in how precipitation timing, magnitude, where the precipitation happens might change in the future. This is a plot that's showing the number of models that agree. So models generally agree that the high latitudes up in Canada, further north, will become wetter in the future. And they generally agree that kind of south of the southern U.S. and Mexico will get drier, but there's this huge area kind of right through the middle of the U.S. where half the models say it's going to get wetter and half the models say it's going to get drier. So that's a big uncertainty. Or it also just reflects the fact that it's noisy. It's a noisy system, and maybe the change isn't that big for that particular thing. So there's a few different topics that I'm going to talk about for impacts. One is temperature and extreme heat. Then this other category of precipitation, drought, and snowpack, so kind of the water resources topic. Here in the Bay Area, we had a focus on fog. I heard that you guys got a good view of the fog today. So it's a big, important feature of the climate here in the region. And so it was neat that we got to kind of think about how is climate change affecting fog. Wildfire is a big one that's on everyone's mind right now because of the really destructive fires that have happened in the last couple of years, and then sea level rise. So I'm going to say a little bit about each of these. So with the temperature and heat extremes, we are able to kind of project down to the regional area. And so in each of these plots, what you're seeing is here's the San Francisco Bay, there's San Francisco, Berkeley's over here, and these are the 9 counties that make up the Bay Area. And so this is the temperature of the average hottest day of year. And then this is the end of the century. So this is like approximately 2080 under the lower emission scenario and under the higher emission scenario. And so the hottest day of the year could increase anywhere from 6 degrees up to 10 degrees hotter. So going from, and here in the Bay Area we have this big gradient where it's much, much cooler in San Francisco and Oakland and Berkeley than it is just a little bit inland. So we have these really extreme microclimates. And the science is showing that it's going to get even hotter in those places that are already really, really hot. With average hottest day of the year, like potentially at 116 degrees. For precipitation, as I was saying, it's a much noisier system, and you can kind of see here's the historical variation in precipitation for the 9 counties of the Bay Area. And so in the future, you see a lot of this continued variability and not a huge trend in the average, and maybe like some slight increase in overall precipitation. But that does mask something else, which is that so while the average precipitation is very noisy and we don't know if it'll go up or down, or it may not do either, there is this growing evidence that individual storms are becoming more intense. And so what's happening with that is that as the atmosphere gets hotter, it can hold more moisture. And so when you have a rain event, more precipitation happens. And so there's much greater agreement among the models that the average wettest day of the year will increase in the future. And so again, this is a similar thing, showing that the average wettest day of the year would increase by maybe 20% under a lower emission scenario and something more like 30 to 40% under a higher emission scenario. So those individual rain events are going to dump more rain, which means more stress on storm drain infrastructure, more potential for floods. And then there's the snow, which I mentioned earlier. There's pretty good evidence that snow will be melting simply because of higher temperatures. And this isn't displaying super great, but what it's showing is the state of California, and the kind of present day we have this very important water resource, which is the snow that falls in the Sierra Nevada mountains. And as the planet warms by end of century, again, this is the higher emission scenario, that snowpack could reduce by something on the order of 80%. And that's extremely important for the way we manage water in California, because it's a Mediterranean climate. We get most of the precipitation in the wintertime, hardly any precipitation at all in the summertime. So that snow is incredibly important because it acts as a natural storage mechanism. The snow slowly melts out of the mountains and fills up the reservoirs, and we can kind of use it over the summer. And so if we don't have that storage mechanism, we'll have to build some other way of storing water, potentially in the groundwater, or building more reservoirs, or just rethink the way we use water. This is kind of the schematic plot that shows, it's really hard to, but this is kind of showing the precipitation happening in the winter, but then the demand for the water happening in the summer. And what's happening with climate change is that the snow melt shifts earlier So because now the snow is melting earlier, so it'll happen there, but then you have this increase in demand from the higher temperatures, and so that difference between those peaks is what you need the storage for. And so that challenge of storage becomes more intense in a world where the snow is melting earlier. All right, so fog. Fog was a really interesting one to look at in this study because, as I mentioned, we have this really extreme gradient in temperature, and that's largely driven by the coastal breeze and fog. And so you guys are experts on HVAC systems and building technologies. A lot of people living in the interior part of the Bay Area don't have air conditioners because it doesn't really get that hot currently. And the big reason for that is because of the fog and the sea breeze. So it's really important to understand, if climate change were to affect fog by either making it go up or go down, that could really change these microclimates and could really change the demand for energy in the region. And this is one where, because our research on the climate system has kind of started from the global system, we don't really understand very well those really much smaller scale dynamics and how it might change. We do know from observations that fog's been declining over the last, say, 60 to 80 years, but we don't know if that's driven by land use change or climate or something else. So that emerged as one of the big uncertainties and areas for more research. We don't really completely understand that one. Then there's the wildfires, and this is just showing historically burned area in those 9 counties of the Bay Area. So a couple big ones in the 60s, but then this is 2017, completely off the charts. I think this is really dramatic, and it just shows how unprecedented the fires that we've been seeing in the last 2 years are from what has just historically happened. And again, this was 2017. In 2018, there were even larger fires. So just these last 2 years have been very, very different. Looking forward, the models typically show that it's because of higher temperatures, lower vapor pressure deficit, that fire risk will increase. So this plot is showing the red means where fire frequency will increase in the Bay Area. The green is where it would decrease. And the thing that is causing it to decrease isn't related to climate, it's related to land use change. So in this particular study, they assume that the urban area was expanding. And so the places where the fire risk goes down is where essentially the urban wildland interface has moved further out to the edge. And so you have more urban areas that are not touching natural areas anymore. And so it kind of highlights how for fire in particular, it's this interplay of land use change and the weather and climate. And then for the final topic here for kind of the regional impacts is sea level rise. And this is an interesting one as well because it's a very, very slow process. So I mentioned that if we stopped emitting all greenhouse gases right now, that the planet's going to continue to warm for, say, 30 years or so. With sea level rise, that process is going to play out over hundreds of years. And that's just because of the very, very slow timescales of ice melting and the ocean warming. And so up to this point, we've observed only about 20 centimeters of sea level rise. So relatively insignificant amount of sea level rise. It has changed the amount of, we do see now when there are king tide events, which are kind of the highest tides that you get per year. Those king tide events are now, a few centimeters higher than they used to be, which means that you have areas that flood during those king tide events that didn't used to flood. But that's really just the beginning, and kind of it has this hockey stick character that it starts off slow, but then it starts to become more extreme over time. And this is also a place where there's different processes that contribute to sea level rise. So one is the warming of the ocean causes the water to just expand. And so that's relatively well understood because we know the physics of how warmer water takes up more volume than colder water. The real wild card here is how much the big ice sheets are going to melt. So the Greenland ice sheet and the Antarctic ice sheet. And so this range here reflects the uncertainty about how quickly and how much of those big ice sheets are going to melt. And the science, the information about those projections has been evolving over time. I don't really want to spend that much time on that one. But we do know that there is quite a bit of infrastructure here in the Bay Area that's built right around the bay. So this is a map. Again, you're looking at the bay here, and each of these colored lines represent different kinds of infrastructure. Like some of them are levees, but there's also roads, natural gas pipelines, train lines, 3 international airports, and all sorts of infrastructure that's built right at the edge of the bay. So all this stuff is at risk for flooding under sea level rise, and then you combine that sea level rise with the more extreme storms and heavy precipitation. And so that's something that's really got the local decision makers very concerned. This map is showing one of the, I'm sorry, I don't know how many feet of sea level rise this is, but it's showing the regions around the bay that are most at risk under rising sea level. And so in this report, we kind of looked at, over here, it's wastewater treatment facilities. And the more orange and red colors you see, the more at risk those wastewater treatment facilities are at different degrees of sea level rise. Here's a 3D look at the Oakland port. So there's the Bay Bridge and this major shipping port. And the more red colors here indicate higher levels of sea level rise. So there's just indicating all this infrastructure that's right there at the coast. So there's 3 take-home messages from this regional look at climate change that I wanted to highlight. One is that our global success in cutting carbon pollution will make a significant difference for the Bay Area. So that point I was making at the beginning, that at the end of the century, it really matters which emissions trajectory we're on. And the impacts could be much more significant, or they could not be as significant, but there are some either way. Again, yeah, that's just looking at the high emission scenario versus the more moderate emission scenario. And again, the high emission scenario versus the more moderate emission scenario for temperature change. The other kind of lesson from the report is that while everyone's affected, there are more vulnerable communities than others. There are groups of people that are going to be more impacted, and there are groups of people that are going to be less able to adapt. So this was a study that looked at different factors that indicate ability to deal with crisis. They looked at socioeconomic factors, education, social isolation, and other factors like that. And so they map for the city of Oakland here these factors, and as it turns out, the communities that are more vulnerable are located closer to the coast, and then the blue here is one of the sea level rise projections. And so how sea level rise or certain flood events are going to affect these communities could be quite different than how it affects communities in Alameda, which is a more middle-class, more middle-class affluent community. And then the third lesson is this importance of land use change. That the way that the choices that we make about land use on the coast and the choices that we make in the urban-wildland interface related to fire risk are absolutely critical for how we manage these risks. So again, the coastal risks and the fire risks are very, very much related to land use planning and how we design buildings also. Can these buildings keep themselves going when the grid goes down? Or are they built with materials that are resistant to fire, et cetera? So now I'm going to switch gears slightly to talk a little bit more about my own research and the group that I work with at the lab on resilience and adaptation. So I run a group that is called Earth Systems and Society, and there's 4 research themes there. One is what we call Earth Systems Modeling at Decision-Relevant Scales. So that's this idea of we've built these climate models that look at climate at the global scale, and we're starting to try to look at more and more detail at a local and regional level to understand how it plays out in cities at a regional scale where it matters to decision makers. Another theme is what we call usability of scientific data. So we're doing a lot of engagement with stakeholders to ask them questions about what information do you actually need, and then taking that to evaluate whether or not the science is able to provide the information that the decision makers are asking for. We have a theme called coupled human and earth system processes, and so that's starting to incorporate more and more the human systems in and their interactions with the environmental systems in models. So things like including cities in models, including agriculture in models, because we manage a lot of the land with agriculture, and that has an effect on the regional climate. And then decision analysis and risk assessment, so doing different scenarios to evaluate, if we build the city to look in this particular way, or if we build the city to look in this particular way, how does that change the risks? So one of the things that we've built as part of this is a urban environmental systems modeling. We're doing that because cities are where the people are, and much of the infrastructure. So a lot of this stuff is playing out in cities, as I kind of mentioned at the beginning. Also, cities make their own microenvironments, right? So this is an infrared image of Manhattan showing the heat that's coming off of all these buildings, either because of the materials they're made of, they've absorbed that heat during the day and they're radiating it out. Some of this might be from the systems inside the buildings that are generating waste heat. So cities significantly affect their own environment through the urban heat island and other effects. And then cities also have a lot of options for adaptation. There's lots of things that could be done to try to mitigate risk. Like there's a lot of interest now in green infrastructure for helping with flood. And I'm going to talk a bit about cool roofs. Before I do that, there's a group here at the lab that's been thinking about kind of how do we apply science to this idea of resilience. And so we've kind of identified some sort of buckets or ways of thinking about this. One is to identify what are the stressors themselves. So it's the extreme precipitation, the extreme heat events, that sort of thing. And then what systems are affected by those stressors. And then we need to think about what the impacts are and of those stressors. So is it loss of the electricity grid? Is it impacts on health, et cetera? And then what are some of the proposed solutions so we can evaluate whether or not how effective they are in impacting those metrics. And then we bring models and data analysis to those problems. And so there's kind of some fundamental science expertise that's involved in understanding the stressors in the systems themselves. There's this critical need for engaging with the stakeholder community to understand what are the impacts, what are the potential solutions. And then there's all sorts of methodological things like analytical methods and the computational infrastructure and sensors that we can kind of bring to the modeling and the data and the analysis. This urban climate modeling system or urban environmental systems model that we're using, this is an example of how we've applied it in California. So you have this gridded model that's looking at the atmospheric dynamics, and it zooms in to ever more detail over these major metropolitan areas, so the Bay Area up here, and then Los Angeles and San Diego down here. And so it's much, much higher resolution over the urban parts, and it's a bit more coarse resolution over the rest of the state and the western US. And then we can apply different external factors to that model. So we can look at different scenarios for how the large-scale climate's changing, different land use scenarios in terms of what do the buildings look like, and then different population scenarios. And then out from that, we get what does the very, very localized climate look like. In this particular model, we're also looking at irrigation water use of the water people are using for landscape irrigation. We can calculate the energy demand with using a relatively simple metric that you might be familiar with, cooling degree days, and then also look at health outcomes related to these extreme heat events. And then we can play around with different adaptation options. So cool roofs is one that we've been very interested in. So this idea of painting the roofs with reflective materials or using reflective materials to radiate energy back out to space. And then this other one, drought tolerant vegetation. So during the drought in California, there were a number of cities implemented these programs where they paid people to convert their lawns that look like this into things that look like this with succulents and rocks instead of grass. And so it definitely reduces water use, but it has impacts on the regional climate as well. So this gives off a lot more heat than a wet lawn gives. So we're looking at that in our models as well. Some of the things that we're not yet looking at, but we're very interested in is the potential for green infrastructure to contribute to groundwater recharge. flood risk mitigation. In Houston, when Hurricane Harvey happened, it's the case that that hurricane was much, much wetter than hurricanes that we've seen previously, but it was also the case that over the last few decades, Houston has really grown and there's a lot more impervious surfaces. So it's again that twin, the climate's changing and the land use has changed, and together they created a lot more risk for flood. And then fire risk mitigation, we're building in the urban wildland interface. So we looked at future changes in heat extremes across the state of California, and we tried to look at this through the lens of not just extreme heat, but heat waves, so multi-day hot events. And so the modeling shows that, and it depends on how you define it. So if you define it in kind of this universal way, you get one answer, and if you define it relative to local variability, so if I live in Phoenix, what I consider an extreme heat day might be different from what I consider an extreme heat day in San Francisco. And so if you do it the locally defined way, it's a little different answer. But kind of the real take-home message here is that if at this scale, cities don't really matter. So if I implemented cool roofs on all the cities in California, you wouldn't see any change in this map because the cities are a really, really small part of the map. But if you zoom in on the urban areas and then you look at these heat waves in a population weighted, so if you look at it through so where the actual buildings are, where people are using their air conditioning, and where people are going to experience the health effects of these heat waves, then if I now look at, this is present day, future without cool roofs and future with cool roofs, the cool roofs have this really dramatic effect on reducing the exposure of people to heat waves. And you can see it here with the cooling energy demands as well. So that, again, this is this cooling degree days metric. And here we looked at change in population. So in all 4 of these scenarios, an increase in population means that there's just going to be more energy demand. But now you add on that a hotter climate scenario, and then a more moderate climate scenario, and then the green is the interaction effect between them. So you have hotter climate and more population. So this is, again, increase in energy demand in the hotter scenario, and then if you implement cool roofs, and then the not quite as hot scenario and cool roofs in that scenario. And in that one, the cool roofs actually can bring you back. You could actually, if you didn't have an increase in population, you could actually have lower energy demand than present day. So it's a pretty big effect. And I'm getting there. I know this is a lot. So the kind of final piece here on this line of research is that we also looked at how the cool roofs affect demand for irrigation. So irrigation demand, the amount of water that plants require to survive, is controlled in a big way by the regional climate. And so when it's hotter, all other things being equal, the atmosphere is more hungry for water, and you need to give more water to the plants to keep them alive. And so the inverse is actually true as well. So if you can cool the local climate with cool roofs, it actually reduces the demand for water to keep the plants happy. So the cool roofs make the albedo go up. It's more reflective everywhere. The temperature goes down. This is kind of on the order of 1 to 2 degrees Celsius decrease in temperature. Again, this is the Bay Area and then Southern California. And then kind of the really interesting result here is that it also brings down the demand for water. Ironically, the opposite is not true. Or I don't know if ironic is the right word, but the opposite's not true. So if you implement drought-tolerant vegetation, if you just stop irrigating, it actually has the opposite effect, that it warms the local climate. So you're not converting that energy into water vapor. It means you have you get hotter air. So cool roofs have this synergistic effect that they reduce demand for water, but just reducing your water use can have an undesired effect in making it hotter. So we're trying to now kind of develop this system, and we think one of the really promising areas is thinking more about urban hydrology, so thinking about flooding and the dynamics of water and how it moves through an urban system, the potential for groundwater recharge and the risks associated with flooding. So this is kind of an area that we're working on now that we think is really important. And so kind of now moving towards a conclusion, I titled my talk, "What does climate resiliency look like?" And I guess it's not really for me as a scientist to answer that question. We can provide the tools and the information, but it really is going to take these kind of partnerships with the public and with different kinds of organizations to define what do we want to be resilient in cities and what kinds of strategies are we going to take to address that. And so here in this Bay Area, we have a number of these really interesting organizations coming along. There's groups committed to public health, to fire. There's this Climate Adaptation Network, which is a really neat organization that has maybe hundreds of different organizations come together, what they call themselves the practitioner community, to sort of talk about what does climate adaptation look like in the region, and the scientists are just one of many partners in that. So to wrap it up, some conclusions or summary. We're at this point in time committed to a certain degree of climate change. It's happening, but we still have an opportunity to avoid the worst possible outcomes if as a global community we can control our greenhouse gas emissions. Those changing environmental conditions pose new risks for cities and for infrastructure, risks that we didn't see before. And land use and building technology, the way we build our buildings, the way we build our cities, is a really important piece of how we're going to be resilient to these changing stressors. And then finally, we need this stakeholder input and collaboration between the science community and the stakeholders in order to define what resilience looks like and identify solutions. So. Okay, I'll start here at the front.
And just to clarify, all of the greenhouse gases, and especially CO2,
yeah.
Is it, whatever we're putting in now, how long is that going to take if we stopped all emissions?
Right.
How long would we be living with the consequences of what's in the atmosphere now?
Yeah.
Would it be hundreds of years, 50 years, thousands of years?
Right. So
how permanent is the change that we're seeing?
It's right. So the carbon that we're burning was put into the earth over millions of years, right? So it's plankton that lived in the ocean and died and went to the bottom of the ocean, and then some small fraction of that became petroleum and coal. And so if we're taking that fossil carbon and putting it back in the atmosphere, the time scale of that carbon being removed from the atmosphere is on a millennial time scale. The point I was trying to make earlier is that if we stop all emissions, we'll see the planet continue to warm for several decades. Then it'll reach an equilibrium, but it's going to reach a new equilibrium. It's not going to come back down to where it was before. It'll stay at that new equilibrium for a very long time. Yeah.
So you talk about the cool roofs, the white roofs. You did your study on the Bay Area. What impact might that have? Is it similar in other areas of the country? And I'm thinking, well, then I got to replace my roof sometime in the next couple of years. Should I go to as light a color as possible?
Yeah. So there's been a number of, this cool roof thing has been studied for a while. I think there are, I've seen maps where it kind of shows where's the net energy benefit good or bad, right? Because in regions of the country where you also heat in the winter, it could increase your need to heat in the winter. So it really does there is kind of a regional piece to where does it make sense to do cool roofs and where doesn't it. But in particular for those really hot extreme heat events, it's I think it can only be a positive for that. But the question is, are you kind of
I'm in Wisconsin.
Okay.
The reality is that my roof is over my attic.
Yeah.
Which, in an ideal world, the attic is going to be at outside conditions.
Right.
temperature-wise anyway. So it's
Yeah.
not necessarily going to have an impact on the home itself.
That's right. Yeah. If you've got proper insulation, then I guess it wouldn't. Yeah. So.
I'm not going to say I have.
It's there.
Yeah. Yeah. Over here.
Would you help me wrap my mind around this? I thought the central problem was that heat can't escape into outer space like it used to. So cool roofs are going to reflect heat back into a trap to some degree then, aren't they?
So the difference is that we have to get into the frequency of the radiation, right? So cool roofs are reflecting sunlight, which is shortwave radiation, and the greenhouse gases trap long-wave radiation. So let's see. So normally what happens is the sunlight hits the surface, that surface warms up, and then it radiates out at a lower frequency. So that lower frequency radiation is what's being trapped by the greenhouse gases. But the sunlight itself can bounce right back out to space. Yeah.
So when the sun reflects off the roof, it's not going to extend out the long wave radiation.
I mean, some of it will. So some of it does as it's coming in through the atmosphere, right? So to the degree that sunlight is hitting clouds and reflecting off of things in the atmosphere on its way in, it'll also do that on the way out. But so whatever sunlight is hitting something on the way out will warm up that in the upper atmosphere rather than right down at the surface.
But at least some of it's going to leave the atmosphere.
Yeah.
Shortwave radiation.
Yeah, exactly. Yeah, and that happens in a big way with snow and ice. So if you look at the planet from space, you see big white regions around the northern latitudes, and so large amounts of sunlight are hitting that and going right back out to space, and that's one of the feedbacks in the climate system. As we're warming, you have less of that snow and ice, and so the planet starts to warm at a accelerated rate because now there's less snow and ice, and that's also why the Arctic is warming faster than the rest of the planet because of that loss of ice. So it's a similar thing, but we could sort of engineer it to go the other way and paint things silver. Yeah.
Is ASHRAE looking at design temperatures in the United States? I know several years ago they changed some of the numbers that they had in their design standards. I'm just wondering how closely they're following and just the frequency of updating that data is.
Yeah, I'm not sure. This is a
Yeah. So I'm not sure how quickly, but the building codes and design guidelines need to be designing HVAC systems for warmer temperatures. How quickly ASHRAE is doing that, I don't know.
Several years ago, they changed the numbers. They
Yeah.
made some. They said they made some account for it. I just wondering if they're really going to
That's a good question. Does anybody else know about ASHRAE's? It's a good question. I'll find out. I'll find out and I'll send you out an email.
yeah.
I think they take the average temperatures as soon as they're available,
But
run
it's
them
still
through a model, and if it
Yeah.
gets big enough,
Right.
that they move the average.
Yeah. But should you be planning for the last 20 years or the next 50 years? Yeah.
HVAC is supposed to last 20 years.
Right. Okay. So the next 20.
What's the average temperature over those 20 years?
Yeah.
So in regards to resiliency, is part of the study oriented towards trying to leverage that aging infrastructure piece and replace it in a more responsive or aiming towards more resilient?
Yeah.
Andy,
Exactly.
Can you repeat the question?
Sure.
I
Yeah.
don't think we heard it back here.
Yeah, so the question was, that in terms of resiliency, as part of what we're aiming to do is sort of inform all this new infrastructure that we're building, and can we build that infrastructure in a way that's built, again, for the next 50 years rather than the last 50 years. And that's certainly our hope, right? That we could get the science to a place where we're not just saying this is how much hotter it's going to be, but we could actually understand how the infrastructure systems would function under these different conditions and help with partners design better infrastructure. That's what we hope, yeah. There's one back here really eager.
It sounds like you do a lot of work on all kinds of things. There's a lot of people that agree. And you're doing such a big area. Have you guys thought about just doing a smaller area, like a smaller town or something else, and and get some rich guy to fund it, you know, move it money or do something, and then all of a sudden, hey,
Yeah.
it's working.
Yeah.
Check it out.
If you know such a rich guy, let me know.
We're in California.
Yeah.
We did Sacramento.
Yeah.
Yeah, I mean, that happened,
Right.
You know,
but you compare the suburbs to Sacramento, so it's also the trees,
Mhm.
right?
Yeah,
It's
yeah.
schools, but there's been a lot of work on neighborhoods that
Yeah.
show the influence.
the area
Yeah.
that you're trying to cover to try to,
Yeah.
how do you do an experiment on something like that?
It's pretty well documented, the cooling stages from cool roofs.
Uh-huh.
So I think there's a lot of field work that actually showed that. And the City of LA has been very active, New
Yeah.
York City,
Mhm.
so there's pretty good information. And again, I can send a few references if you want.
Yeah.
I'd like to just get a sense of the group, because cool roofs was something that we kind of floated through. We were maybe gonna have somebody speak about it, and we thought, no, it's too far afield. If we had a speaker, say next year on cool roofs, how many would find that interesting? Is that, yeah? All right, good, we'll keep that in mind.
You know, just the opposite of a cool roof is like last night. You just showed it, the heat island, that picture right there.
Mhm.
When we went to Chinatown last night, we noticed about a 10-degree gain in temperature as we got off the train. Or when did we get off the ferry there? I was in my previous life. I was a weather guy in the Air Force, and I looked at the study of Atlanta as
Yeah.
it blew up. The just to the northeast of it, in the summertime, thunderstorms would develop in the northeast
Yeah.
just because it was a macro scale low pressure over that heat island. So opposite of heat, opposite of that dense concrete infrastructure, white roofs just make sense that it go the other direction.
Yeah. So that in our study, we had the advantage of we were looking at California cities in the summer when there's no rain. But there are studies that have kind of shown that exactly what you're saying, that the dynamics of how storms move through, over St. Louis where it's really flat all around there, but then you have this heat island, this bubble of heat, and it can affect how the precipitation and the storms go. Yeah. I'm gonna go with this. Yeah.
Okay, so I've been following the climate research for some time. Obviously not an insider in how it works and all that, but I've noticed, and I've been coming to these institutes for several years now. We get presentations like this, and what I've noticed over the years is that there's been a shift, not only in these presentations but just in general, in the message, in the action verb. Before, earlier on, it seemed more hopeful, and like if we do this, we can win. And now in this particular institute, we've heard you're talking about resiliency, and one of the other presenters we had talked about drawing down. This sounds to me like if I could summarize like batten down the hatches. So we've evolved. We've moved from one message to another. Maybe there's been more. I mean, I'm not privy to all the information maybe that you are. My question is, so we've seen this evolution. What is the next message that we're going to hear? What is the next thing?
That's a good question.
I don't know if that's a start.
Yeah.
Move to higher ground.
Right? Yeah. I mean, so I get a question often. This might sound a little depressing, but I get a question often like, have we passed the point of no return? And my answer now is every day we pass a new point of no return, which maybe the hopeful flip of that is that every day we have an opportunity to not pass another point of no return. But every time, as the emissions build, we're committed to a new level of ultimate climate change. But it also is the case that there's always going to be, maybe 50 years from now, we're on this pathway, but there's going to be another place where we still have the option of getting there or not getting there. So I think there's a little danger in some of the debates, like once we cross 2 degrees, then everyone, we've lost. Well, 2.5 degrees is going to be a lot better than 3.5 degrees or 4 degrees or 6 degrees. So there's what's that? Yeah, so it's a compared to what? So I think, but I do think you're right that it shifted from, it's been, for a long time it was kind of abstract, right? Like this might happen, this is going to happen if we don't do something. Now it's happening and we still need to do something. So we need to adapt and mitigate, not just mitigate now.
Yeah, I'm wondering what happens
Yeah.
Then we see more of the effects or something.
Uh-huh.
we react to it. I don't know.
Yeah.
So a comment and a question. The comment is that it appears we need to work on infrastructure. There's talk of it at the national level. But we need to almost do scenario-based infrastructure, depending on, what that future looks like.
Yeah.
My question is, on your last point there that you really didn't spend too much time on.
Yeah.
I read a study of a kind of a climate conversation in the city of Edmonton in Canada, which was very interesting. Climate change is defined as a wicked problem or a super wicked problem for various reasons. And that whole stakeholder issue, we're seeing people trying to engage conversations locally,
Yeah.
at the city level. We have a secret national energy policy in the U.S. That we can't talk about. How do we, is anyone really looking at how we engage stakeholders to really begin to get serious about the conversation?
Well, that's part of what, so this Climate Readiness Institute that I'm deputy director of, it's part of, essentially the mission of that organization is to bring the research community together with the practitioner community. Of course, that's kind of predicated on that there's a willing group of practitioners who want to engage, which we've found is the case. So there's all kinds of water managers and agricultural extension specialists and people who are kind of in the trenches thinking about this stuff. They want to design the infrastructure to be resilient, but they need information. So I that's where I've seen a really fruitful collaboration. And I think that kind of getting back to the point about the story has changed, I think it's a good, it's unfortunate that we got to this point without, just stopping the emissions. But now that we can see the adaptation challenge more clearly, I think it motivates people to really think about how do we keep this from getting worse? Because once you start talking about, oh yeah, that road's going to be underwater, or what does this mean for extreme heat in my community, or how we're not going to have snow anymore. So once you start thinking about those impacts in a much more clear way, I think it changes the conversation about the mitigation piece because it makes it much more concrete. Yeah.
So just to follow up on your comment, Peter, the cities are doing a lot of this 80 by 50. So a lot of cities are trying to reduce greenhouse gas emissions by 50%, by 80% by 2050. And there's cities throughout the world, cities throughout the United States. So a lot of the action is local these days. But my question to you is about cost-benefit analysis. And you talked a lot about, I'm just curious if you do cost-benefit analysis, and if you could talk a little about the economics of these investments for resilience.
Yeah. I guess I have thought about it in, terms of, I guess I'm personally of the view that cost-benefit analysis can be really, it's hard because you've got things that are really different that you're trying to put them all in money terms, So, is it, how do you monetize the impact on health in a low-income community versus another community? And yeah, I guess, I have one response is, I like to think of it more in kind of a multi-objective risk-based framework where you have trade-offs between things. And I guess one of those trade-offs is how much is it going to cost? Then I guess the other thing that comes to mind is there have been a number of studies like the Risky Business Report where they looked at quantifying the costs of climate change, for different impacts. So what will all these health impacts cost in terms of hospitalizations and that sort of thing? So I guess it's been less my work to put it to monetize it, but certainly there's a lot of that out there. And I guess there's also kind of the perspective that the transitioning to a green economy, low carbon economy doesn't necessarily mean that it's going to be incredibly costly, that it can create jobs and be a source of economic development. So, yeah, I guess that's kind of my
Paul
piecemeal
today
response.
Paul Matthew talked to this group about financing green buildings, energy efficiency buildings, and that's one of the areas where the people in this room can actually help, achieve significant improved performance in building stuff. So that's one of the strategies.
Without even going into the difficult areas that are more difficult to quantify, like healthcare, but your first few slides talked about the cost with respect to the catastrophic events.
Yeah.
Take the known variables. Easily quantifiable. The cost benefit.
It's true. Yeah.
Well, and what's in a sense driving some of that risk assessment is insurance industry.
Yeah.
Bloomberg is working on that.
Yeah, it's interesting with the insurance industry is that because they update premiums on a they're looking on a pretty short time window, so what I've noticed is that they want to know how things changed to date, so they're very interested in how is today's climate different than 20, 30 years ago. They're not so much interested in what's it going to be in 30 years because they're going to just keep changing what they charge as the climate changes. But it's now at the point where they do want to know what should our 100-year flood map look like? Should we still be using this 100-year flood map that we made based on data from 40 years ago? Or should it be completely different now? Yeah, back there.
So, you said a lot of people agree on this in a room with you. How many people, what I'm interested in is, how many people do you, on average, maybe put in the room with you that disagree? That can at least play the game, fight with numbers and models, to really bang out, a solid concrete thing, or are you already doing that?
I guess, I mean, I think that,
debate,
what's that?
Just a little well-rounded, I mean, how is that agreement process work? Because you used it quite a bit, that a bunch of people had agreed on the same kind of topic.
Right.
Are you putting people in the room that disagree with you and that have the intellect to go at it? Or do you guys switch sides and try to play like a chess game with each other to try to drive a true focus through it?
Yeah, well, I would say the scientists are pretty naturally disagreeable folks. And I think a lot of science is about kind of poking holes in theories and challenging things and really proving things in the most rigorous way. So I tried to highlight places where, for instance, our models agree and don't agree on particular outcomes. For the precipitation, that it's less certain, or like with fog, we don't really know that much about whether or not we do see that fog has been changing in the Bay Area, but we don't have a solid explanation for why it's changing. Is that driven by land use? Is it driven by climate change? Is it driven by something else? So, I think that I would say that all of my colleagues are very careful about, what do we have confidence in and what do we not have confidence in. I think a lot of debate comes in, when we get into the engaging with the practitioner community and, where you have different interests about what is important. Like if we know that the shoreline is going to be more and more flooded around the bay, but what does that mean? You've got certain groups that would prefer to build a seawall and just, keep it from happening. And then there's this extreme thing that you could do, which is you could actually build a seawall at the mouth of the Golden Gate Bridge and turn the bay into a lake. And then you could prevent sea level rise from affecting the whole inside of the bay. But is that something that we want to do? That's kind of, I think, a place where differences of opinion are going to come in. And that's not a scientific question. That's a social, political question of what are our values and how should we respond to this? But in terms of the science of what do we know and not know, there are things that we have high confidence in, and there's things that we have low confidence in. And it's more of a kind of objective statement about that.
And if it does flood, you can send all of your bucket boys over here to cover the water.
So basically what you're saying is San Francisco is trying to build a wall.
Yes. Build the seawall. Yeah. That's good. I don't know if you can top that, but yeah.
To end on a, nobody can follow that.